Abiogenesis, or biopoiesis or OOL, is the natural process of life arising from non-living matter, such as simple organic compounds. It is thought to have occurred on Earth between 3.8 and 4.1 billion years ago, and is studied through a combination of laboratory experiments and extrapolation from the genetic information of modern organisms in order to make reasonable conjectures about what pre-life chemical reactions may have given rise to a living system. The study of abiogenesis involves three main types of considerations: the geophysical, the chemical, and the biological, with more recent approaches attempting a synthesis of all three. Many approaches investigate how self-replicating molecules, or their components, came into existence. It is generally accepted that current life on Earth descended from an RNA world, although RNA-based life may not have been the first life to have existed. The Miller-Urey experiment and similar experiments demonstrated that most amino acids, basic chemicals of life, can be synthesized from inorganic compounds in conditions intended to be similar to early Earth. Several mechanisms of organic molecule synthesis have been investigated, including lightning and radiation. Other approaches focus on understanding how catalysis in chemical systems on the early Earth might have provided the precursor molecules necessary for self-replication. Complex organic molecules have been found in the solar system and in interstellar space, and these molecules may have provided starting material for the development of life on Earth. The panspermia hypothesis suggests that microscopic life was distributed by meteoroids, asteroids and other small solar system bodies, and that life may exist throughout the universe. It is speculated that the biochemistry of life may have begun shortly after the Big Bang, 13.8 billion years ago, during a habitable epoch when the age of the universe was only 10 to 17 million years. Panspermia hypothesis answers the question of whence life, not how life came to be. It only postulates the origin of life to a locale outside the Earth. Nonetheless, Earth is the only place in the universe known to harbor life. The age of the Earth is about 4.54 billion years. The earliest undisputed evidence of life on Earth dates at least from 3.5 billion years ago, during the Eoarchean era, after a geological crust started to solidify following the earlier molten Hadean. There are microbial mat fossils found in 3.48 billion-year-old sandstone discovered in Western Australia. Other early physical evidence of a biogenic substance is graphite in 3.7 billion-year-old metasedimentary rocks discovered in southwestern Greenland, as well as remains of biotic life found in 4.1 billion-year-old rocks in Western Australia. According to one of the researchers, if life arose relatively quickly on Earth, then it could be common in the universe. Early geophysical conditions. Based on recent computer model studies, the complex organic molecules necessary for life may have formed in the protoplanetary disk of dust grains surrounding the Sun before the formation of the Earth. According to the computer studies, this same process may also occur around other stars that acquire planets. At first, it was thought that the Earth's atmosphere consisted of hydrides, methane, ammonia and water vapor, and that life began under such reducing conditions, which are conducive to the formation of organic molecules. During its formation, the Earth lost a significant part of its initial mass, with a nucleus of the heavier rocky elements of the protoplanetary disk remaining. According to later models, suggested by study of ancient minerals, the atmosphere in the late Hadean period consisted largely of nitrogen and carbon dioxide, with smaller amounts of carbon monoxide, hydrogen, and sulfur compounds. As Earth lacked the gravity to hold any molecular hydrogen, this component of the atmosphere would have been rapidly lost during the Hadean period, along with the bulk of the original inert gases. The solution of carbon dioxide in water is thought to have made the seas slightly acidic, giving it a pH of about 5.5. The atmosphere at the time has been characterized as of gigantic productive outdoor chemical laboratory. It may have been similar to the mixture of gases released today by volcanoes, which still support some abiotic chemistry. Oceans may have appeared first in the Hadean, as soon as 200 million years after the Earth was formed, in a hot 100 degrees Celsius reducing environment, and the pH of about 5.8 rose rapidly towards neutral. This has been supported by the dating of 4.404 Ga-old zircon crystals from metamorphosed quartzite of Mount Naria in Western Australia, which are evidence that oceans and continental crust existed within 150 ma of Earth's formation. Despite the likely increased volcanism and existence of many smaller tectonic platelets, it has been suggested that between 4.4 and 4.3 Ga, the Earth was a water world with little if any continental crust, an extremely turbulent atmosphere and a hydrosphere subject to intense ultraviolet light from a Tauri stage sun, cosmic radiation and continued bolide impacts. The Hadean environment would have been highly hazardous to modern life. Frequent collisions with large objects, up to 500 kilometers in diameter, would have been sufficient to sterilize the planet and vaporize the ocean within a few months of impact, with hot steam mixed with rock vapor becoming high-altitude clouds that would completely cover the planet. After a few months, the height of these clouds would have begun to decrease, but the cloud base would still have been elevated for about the next 1,000 years. After that, it would have begun to rain at low altitude. For another 2,000 years, rains would slowly have drawn down the height of the clouds, returning the oceans to their original depth only 3,000 years after the impact event. The earliest biological evidence for life on Earth. The earliest life on Earth existed before 3.5 billion years ago, during the Eoarchean era, when sufficient crust had solidified following the molten Hadean. Physical evidence has been found in biogenic graphite in 3.7 billion-year-old metasedimentary rocks from southwestern Greenland and microbial mat fossils found in 3.48 billion-year-old sandstone from Western Australia. Evidence of early life in rocks from Achilea Island, near the Isua supracrustal belt in southwestern Greenland, dating to 3.7 billion years ago, have shown biogenic carbon isotopes at Strelley Pool, in the Pilbara region of Western Australia. Compelling evidence of early life has been found in pyrite-bearing sandstone in a fossilized beach that showed rounded tubular cells that oxidize sulfur by photosynthesis in the absence of oxygen. More recently, geochemists have found evidence that life likely existed on Earth at least 4.1 billion years ago, 300 million years earlier than previous research suggested. In the earlier period between 3.8 and 4.1 Ga, changes in the orbits of the giant planets may have caused a heavy bombardment by asteroids and comets that pockmarked the Moon and the other inner planets. This would likely have repeatedly sterilized the planet, had life appeared before that time. Geologically, the Hadean Earth would have been far more active than at any other time in its history. Studies of meteorites suggest that radioactive isotopes such as aluminium-26 with a half-life of 7.17 times 105 years, and potassium-40 with a half-life of 1.250 times 109 years, isotopes mainly produced in supernovae, were much more common. Coupled with internal heating as a result of gravitational sorting between the core and the mantle, there would have been a great deal of mantle convection, with the probable result of many more smaller and much more active tectonic plates than now exist. The time periods between such devastating environmental events give time windows for the possible origin of life in the early environments. A study by Kevin A. Marr and David J. Stevenson shows that if the deep marine hydrothermal setting provides a suitable site for the origin of life, then abiogenesis could have happened as early as 4.0 to 4.2 Ga, whereas if it occurred at the surface of the Earth, Abiogenesis could only have occurred between 3.7 and 4.0 Ga.